There you go. Good evening and welcome to our first virtual MADIA manufacturing meetup. Hope you're all safe and well. I'm Bruce Lathrop, a member of the MADIA board, and I'll be introducing our presenter. But first, I want to thank Brenda Trainer, who is helping with this meetup. Brenda will be moderating the chat and live questions. Our presenter will be answering questions after his presentation. For those unfamiliar with Zoom, you can click on the chat at any time at the bottom of your screen to enter questions. Brenda will be reviewing the chat questions at the end of the presentation so that the presenter can respond to them. At that time, the presenter will also be taking live questions. You're all now muted, so if you have a question, raise your hand and Brenda will unmute you, and then you can ask your question. Before we start the presentation, I wanted to tell you a little bit about MADIA. We are a 501c3 educational organization centered at the heart of San Gabriel Valley in California. Our mission is to ensure the region's technical, scientific, and industrial workforce is connected and has the tools they need to be successful by providing educational programs such as this on entrepreneurship, business finance and operations, and technology development and commercializations in settings which encourage networking and collaboration among our members. Our next meeting will also be part of the MADIA Manufacturing Week and will be March 10th, next Wednesday evening, featuring Me Industries and Darcy, who is just introducing herself. They make fog cooling, disinfecting, and special effects technology. If you have any feedback on this program or ideas for future programs, please send comments and suggestions to email@madiatech.org. Stay online after we're done and grab your favorite beverage, and we'll have some additional networking. I'll now turn to introducing our presenter, Dr. Joseph Gold. He received his PhD in cell and developmental biology from Harvard University in 1991 and was a postdoctoral fellow at UCSF in the Laboratory of Radiobiology and Environmental Health. He subsequently worked at Geron Corporation for 16 years, where he directed basic research into stem cells and their therapeutic applications, with a strong emphasis on cardiovascular disease and diabetes. Dr. Gold served at Stanford's Cardiovascular Institute as Assistant Director of Translational Research from 2012 to 2016, working to bring cell therapies for heart disease to the clinic. His current role at City of Hope is Senior Director of Manufacturing and Co-Director of the Center for Biomedicine and Genetics, a GMP facility that helps researchers move their novel cell and gene therapies to the clinic. This role allows him to apply his 30 years of experience in cell therapy development to truly translational work that will impact cell and gene therapeutics for years to come. So please welcome Dr. Gold.
Anyway, thank you very much. I really appreciate the invitation and the chance to get to tell you about what we're doing at the Center for Biomedicine and Genetics at City of Hope. And I realize I shared an outdated bio. I'm not the co-director. I'm the director of the Center for Biomedicine and Genetics. And what we do there is manufacture a variety of experimental cell and gene therapies, which are being used in clinical trials. And I'm going to spend some time actually focused on the work we're doing with viruses, particularly for oncology. And that's where my title of Fighting Fire with Fire comes from, because we take some pretty nasty viruses and turn them into tools to tackle some pretty devastating diseases. And so along the way, we're going to hit a bunch of topics. Let's see if we can advance this. Hit some major topics here. You know, why is CBG different from the research facilities that most of you are thinking of? What do we make? How do these therapies work? Which means I'm going to give you a crash course in some aspects of the immune system and viruses and cancer. How do we actually manufacture them? And what do we think is coming next when it comes to experimental therapies? So CBG is a GMP facility, meaning a good manufacturing practices facility. And that may seem silly because who wants to follow bad manufacturing practices? Why would you even have to mention that? But the truth of the matter is that to be a GMP facility means that you adhere to certain practices and certain standards. And they're very different from a research lab, even a very good research lab, because we have different goals. For example, in a research lab, a scientist can use any material they can order from a catalog or make themselves or borrow from the lab next door. But all the materials that we use have to be things which are extremely safe to put into human beings at some point. We have to understand where they came from, how they've been stored. We have to control them very carefully once they get to us to make sure they haven't been adulterated or tampered with in any way. We have to understand where every bit of that product is used so we can track it if necessary. And that's what the QA group does. When it comes to the actual manufacturing process, in a basic research lab, it's typically one scientist working on their own project, which of course is appropriate, but anything a basic research lab can do with one person, I have to do with two people, because we have to have one person performing the activity and someone else who's literally standing there with a clipboard, making sure that every setting is appropriate, all the calculations are proper, the time intervals are correct. Said to pipette it up and down 10 times, it wasn't 9 times, and it wasn't 11 times. It's just that level of attention to detail that we have to do. We also tend to have much more elaborate gowning to protect the product from us more than us from the products for the most part. And last of all, anything we do undergoes really exhaustive testing. It's not just the materials. Anything we're making, we're taking measurements along the way to try to understand how the process is going, to see if it's going off track or not. And when we're done, we test these products as extensively as we possibly can to try to make sure they're as safe and efficacious as we know how to do it. And the whole principle behind GMP is that what you can't exclude by testing, you exclude by your practice. So you keep out any practices or materials that you could introduce a problem that you wouldn't be able to detect later. So it's an all comprehensive kind of process, and it may sound a little OCD. You may ask, why do we have to do it this way? And in order to explain that, I want to talk about a couple incidents in history, and we're going to talk mostly about some real tragedies, but I also want to introduce you to a real American hero you should know about. So one of the precipitating incidents here was back in 1937, and the company S.E. Massengill was trying to figure out a way to take their antibiotic sulfanilamide, which is used to treat strep throat, and they wanted to make an oral formulation of it. But the problem was it wasn't particularly soluble in water. But they found that they could dissolve it in diethylene glycol, which dissolved it and also gave it a sweet taste. So they did it, shipped it out, and hundreds of people, mostly children, died horrible deaths because diethylene glycol is extremely toxic to the kidneys and liver, and there was no requirement for them to test it before they did that. And then in 1960, we're going to talk about the tragedy and the hero. The hero is Dr. Frances Oldham Kelsey here, who more people should know about. She was a PhD pharmacologist, and she started working for the FDA back in the early 60s. And in fact, the only reason she got her job was because when she submitted her resume, somebody thought that Frances was a man's name, so they hired her. Lucky for us, they did, because in 1960, she was reviewing an application from a big company, Richardson Merrill, who wanted to market thalidomide in the US. And thalidomide was an anti-nausea drug, which was supposed to be very safe to be used in pregnant women. And it was been used all over the world in lots of countries. But when it came to the US, they expected the FDA to just rubber stamp the approval. And Dr. Kelly said, well, no, I need to understand more about this. There are some studies you need to do. I'm concerned about the nervous system. I'm concerned about this being transferred to the placenta. I don't think this is safe yet. And they put pressure and they push, who is this silly woman who's keeping American commerce in check? This is ridiculous. But she held her ground, and thank God she did, because we know all around the world, babies were born with really severe limb deformities as a result of their mothers having taken this drug, but she kept it out of the country. So that's why we adhere to the standards which we're using now. So let's talk about some of the things we're doing at CVG and why we're doing them. We'll start with cell therapies. There are a whole lot of diseases or injuries that really come about because of the loss of a particular cell type or the loss of its function. And you're all familiar with a lot of these things. Type 1 diabetes, the beta cells of the pancreas die off. Parkinson's disease, a specific subclass of neurons in the brain that make dopamine that die off. And heart failure, because your heart doesn't regenerate at all, the heart eventually can't compensate for damage and loses the ability to pump effectively. So a lot of these conditions here come about because cells either don't regenerate or regenerate very poorly after injury or illness. And of course, we could treat some of these things with transplants. I mean, you can cure heart failure with a heart transplant, but we know there's a big shortage of donors, and it's not a simple process by any means. And in some cases, it's not that the cells are misbehaving, it's that they don't have the intrinsic function you want. I mean, it'd be great if we could take your immune cells, which are designed to tackle infections, and instead turn them on your cancers instead. So the question is, how can we go about doing this? And to make things very simplistic, if you're looking for new sources of cells, You could either go to the patient themselves in some cases or to another donor. And if you're working from the patient's own cells, it's an autologous therapy. And if it's something coming from a third-party donor, it's called an allogeneic therapy. And there's certainly lots of examples of both, and there's examples of treatments which use both modalities. Bone marrow transplants. Some people who have cancer, they'll take the bone marrow, they'll essentially clean it out of their residual leukemia cells and put it back in. So that's an autologous transplant, their own bone marrow back into them. Contrast that with an allogeneic bone marrow transplant, where you take a well-matched donor and put it into someone whose bone marrow was destroyed by chemotherapy. That's an allogeneic transplant. And they both have their pluses and minuses. In the case of an autologous therapy, the downside is that if you're treating 100 patients, you're doing something 100 different times. You have to make that therapy each time. And just as no two people are alike, no two cells necessarily behave exactly the same in any kind of large-scale production process. So what works really well for patient A may not work as well for patient B. And you have to test each one of these batches because it's individual patients every time you make it. The plus side, of course, is that it's a perfect immunological match. So you don't worry about any level of rejection here. In the case of an allogeneic therapy, well, there's less variability because you're only working off one or maybe just a couple sources of cells. So you only have to test these banks, and you can treat a whole lot of patients. Now, the downside is, of course, that immunosuppression may be required here. And it's not necessarily just that the recipient may reject the transplanted cells. If you're transplanting immune cells, it's quite possible that those cells will attack the recipient. That's what we call graft versus host disease. So it's a really thorny problem, which you may have to tackle with very powerful immunosuppressive drugs, which could have very severe side effects in some cases. So when we do cell therapies at CBG, there's a lot of different sources, and some are autologous therapies and some are allogeneic therapies. And for example, we'll work with one type of cell called a mesenchymal stem cell. And in some cases, we're starting with cells which we isolate from donated placentas, and we take these cells and we grow them up and prepare them to be used in therapies to try to suppress graft versus host disease. So if somebody's got a bone marrow transplant and that's creating a problem, we're hoping these cells can shut that down. We've also done a large phase 3 trial production where we took autologous MSCs from a patient's bone marrow, isolated them, grew them, treated them in various ways, put back in the patient to try to halt the course of their ALS, which is a devastating disease with very few treatments right now. We've worked with different types of neural stem cells for various reasons. In some cases, they were genetically modified to try to treat ALS in a separate trial. We've used them and we're using them in a trial to try to stop different forms of blindness. And I'm going to talk later on about a really interesting application where we actually infect them with the virus and use them to try to treat brain cancer. We're working with a type of immune cell called a natural killer cell in some immunotherapies, and I'll touch on that later too. And my facility is really known for its work with pluripotent stem cells. And a pluripotent stem cell is unusual that it has the ability to turn into any cell type in the body if you know how to make it behave. And you've probably all heard of embryonic stem cells. That's one example. There's another type also. But here, for example, I'm showing you some of the heart muscle cells we made to try to treat heart failure in a clinical trial that's going to be starting up soon. And we've made other derivatives to treat another form of blindness and to treat stroke and a pediatric condition. So there's a lot of different potential sources for these cells, and they're being employed and deployed in various ways for different diseases. So let's turn to viruses. And I may switch back and forth between saying viruses and viral vectors, and I should define that at the outset. A viral vector is a virus which has been modified to serve as a vector to deliver a therapeutic payload. So it takes advantage of the fact that viruses they're molecular parasites. They can't do anything on their own. They can infect cells, but they rely entirely on that cell's host machinery to make more copies of them. Some viruses give you transient and not particularly serious infection, the cold virus, right? Vaccinia virus is something which we can use as a vaccine because it infects and eventually can be cleared out by the cells. Some viruses are much more serious. Obviously, COVID is one example. Other things are viruses like HIV, which permanently modify your genome. They infect T cells, and there aren't a lot of viruses that do that effectively, but HIV does, and they can do that, and they inject their payload, and it's permanently then integrated into the DNA of the host cell in that case, so it's a permanent change. The good thing is that with appropriate engineering, we can replace the parts of the virus that cause the disease-causing genes, with some kind of therapeutic payload. And if we do this properly, we can preserve other aspects of the virus we want, like the ability to transfer that material into cells. So in the perfect case, we have a virus that can introduce the genes we want into a cell, but not keep replicating. It's a one-time shot that doesn't then explode throughout the body. So that's very important to know that we can do that. So let's do a quick and overly simplistic summary of some parts of the immune system in cancer, because it's going to be important later on. So, most of you know that the immune system has a lot of different ways to fight infections, but two of the main sources it uses are B cells and T cells. And B cells are the cells that produce antibodies, and T cells are cells which attack infected cells. And one of the real differences here is that antibodies are designed really mostly to try to stop an infection before it starts. So for example, the perfect COVID vaccine would cause your body to produce antibodies that will bind up the virus before it can get in your cells. Now, there are very few perfect vaccines out there. So you also want some degree of a T cell response, because in that case, once your cells are infected, the cells are then producing these foreign proteins that come from the viral genes. And T cells have the ability to recognize those cells and kill them. And the way they recognize these cells is by virtue of something on the surface of the T cell called an antigen receptor. An antigen is just a fancy word for an immune target. In this case, it's a viral protein. But these receptors are really highly specific. So a receptor can bind to one very specific target, and when it does, it essentially activates that T cell. It makes it start dividing, and it turns on all its killing mechanisms to destroy the cell that is expressing that viral gene. And while it seems really odd, it seems like that what your body should do in response to an infection is create new cells to fight that. In reality, all the cells your body has to fight infections are already present there. They're dormant. You've got millions and millions of T cells and B cells in there just waiting to be activated. And in some cases, they will never be activated. You may never encounter the disease, or they may randomly be designed to attack something which is just never made. But in some cases, they're just not responding appropriately. We'll talk a little bit why that might be later on. But they're all there, they're all present. So if you could awaken, the sleeping giant somehow, you'd be able to do a lot of things you possibly can't have the body do now on its own. So cancer cells, we know, arise through mutations, and these mutations lead to uncontrolled growth. And sometimes these mutations lead to changes in proteins that could alter their function. So for example, if a protein's normal job is to serve as a brake on cell replication, you could be cutting that brake line. Or if it's meant to turn on like an accelerator pedal at different times, you could jam it on. But the fact is that a lot of those changes wind up changing the physical shape and the appearance of that protein in ways which should make it look foreign. So the question is, why isn't your immune system then responding to these new foreign antigens? They don't look like normal cellular proteins anymore. So why doesn't your immune system attack them? And if they don't, is there a way we can re-educate your immune system to actually attack cancer cells? And that's going to be something I'm going to talk about in more depth. So one way to use the immune system to fight cancer is what you'd call a cancer vaccine, but it doesn't really work the way that, say, a COVID vaccine does. As I mentioned, COVID vaccines are designed, or any kind of vaccine, are designed in the perfect world to stop the infection in the first place. So you give it to people before they have the infection. This type of cancer vaccine is designed to be a therapeutic vaccine. So it's once somebody already has cancer. And let's say someone has a cancer and they've got a mutation in their p53 gene, which is a gene which normally controls cell growth. And when that gene is mutated, the cancer cell then grows out of control. But again, it changes the appearance of that p53 gene. It looks abnormal. So Don Diamond at City of Hope came up with a way to take an otherwise harmless virus, a vaccinia virus in this case. It's actually a strain called MVA, modified Vaccinia ankara. And what he does is he's cloned into just a short fragment of that p53 gene, not enough to cause the function, but just to show the appearance of that mutated portion. And the idea is this virus is then given to these cancer patients, and it should stimulate their immune system, wake it up essentially, and say, hey, pay attention, start attacking cells that you see with this mutation, which theoretically then turns them against their cancer. And this is in clinical trials at City of Hope now and some other places. And there are other people trying to come up with cancer vaccines like this with different platforms. Another way to fight cancer with viruses really comes by upgrading your own immune cells. And if you recall, I talked about those receptors that T cell have. The antigen receptors are just T cell receptors. So they stick out through the surface of the cell, and that dashed line represents the cell membrane. But you can really divide them into two very big parts: the part that binds the antigen and the rest of the molecule. The rest of the molecule activates that T cell. So once the binding occurs, it transmits a signal through the rest of the molecule, which makes that T cell go to war, essentially. But it turns out that these T cell receptors are really highly modular, meaning you can swap out different antigen binding sites. So on the left-hand side, you might have a T cell receptor which is designed to bind a COVID protein, let's say. But you could change out that part which binds the COVID protein instead for something that maybe binds a protein on the surface of a cancer cell. So in theory now, when this T cell receptor is introduced into a T cell, this new chimeric antigen receptor, or CAR, we call it, it would then only react against the particular cancer cell carrying that mutated protein and attack it. And this can be used in a couple different ways. You may have heard of CAR T cells. They're a new and very successful type of therapy, at least for some types of cancer right now. They're really effective at treating some things like B-cell lymphomas, and we're trying to find ways of making them equally effective in other types of cancer cells. And we can talk about why that is later on if there's time. But right now, it's an autologous therapy, which means you take a patient with the right form of cancer, you isolate their T cells, and you infect them with a modified HIV, a modified lentivirus, which encodes that chimeric antigen receptor against the cancer protein, grow them up, put them back in the patient, and it attacks the cancer cells. And in a lot of patients, it's actually cured these diseases. So that's great, but this is one of those bespoke therapies. So you have to do it for each individual patient. It takes a while. Sometimes it's hard to get enough T cells from patients because they're very sick. They've undergone a lot of chemotherapy. Sometimes they don't grow up so well. And you have situations where patients are so sick they can't wait the 4 to 6 weeks to actually have this product ready to go back into them. So this kind of CAR T work, which has been going on at City of Hope for a while, by people like Steve Foreman and Christine Brown, there are other people who are trying to come up with a more sort of off-the-shelf approach. And the problem with the sort of an off-the-shelf approach using T cells is that T cells have a couple things that make them difficult here. One, for various reasons, the host immune system really sees them very well and can wipe them out. But the other thing is that if I'm putting in T cells from me into you, there's a real strong possibility my T cells will treat you as foreign and cause graft versus host disease, which can be lethal. So there are people who are trying to work with other types of immune cells. And there are people like Mike Caligiuri and Jinhua Yu at City of Hope, among others, who are starting with a different type of immune cell called a natural killer cell. And this is a cell which, for various reasons, the recipient immune system doesn't see it very well, so it can persist longer, but it also doesn't have the ability to attack and cause graft versus host disease. But if you put the appropriate CAR receptor into it, it will actually trigger a response against the cancer cell. So it activates sort of a latent killing program, but it's a safer cell in some ways. And at City of Hope, what we're doing in my facility is we start with umbilical cord blood. We isolate NK cells from these donors, and we grow them up and we modify them in various ways. And these are going to be used in clinical trials to try to treat various forms of cancer, including some forms that CAR T cells don't seem to be able to hit. So another way to use viruses is you can think of it as turning a virus into an arrow, a direct weapon. We make different types of viruses, which are referred to as oncolytic viruses. And this means they lyse, they kill cancer cells. And the way this works is that there are different types of viruses out there, and they carry key genes. And one of these key genes gives them the ability to replicate within cells. And if you took that gene out of the virus, you'd have something which can still infect and get into the cell, but it can't do very much once it's in there. So if you take a virus like this and you remove that particular gene, it can only continue to grow and replicate and kill if it gets into a cell which can replace that function. And a lot of cancer cells have mutated genes that sort of create that function. So these are called oncogenes. Genes get mutated and cause cancer. A lot of these oncogenes can essentially complement the missing gene within the virus. So you could take a virus like this and shoot it into somebody's circulation. And yeah, it might infect all over their body, but it can only continue to replicate and divide and grow and kill in the actual cancer cells that have the appropriate oncogene function in that. So we're making a couple different varieties of this at City of Hope. For Dr. Yuman Fong, we're making this out of a modified version of a pox virus. And for Dr. Jinhua Yu, we're using a modified version of herpes simplex virus. And again, these will be used in clinical trials in various places. Some of these oncolytic vectors are going to go into trials in Australia, and some will start out in the US instead. So this is a whole nother approach to fighting cancer with viruses. This one is a little complicated, but it's pretty cool. So let's talk about it. I call this the Trojan horse strategy. And one of the difficulties in treating brain cancer is that your body has evolved some pretty powerful ways of keeping things away from the brain, whether it's viruses or bacteria or molecules it doesn't want in there. It's called the blood-brain barrier. So what that means is that things which get in your circulation, which can spread throughout your body, don't really get into your brain very effectively. And the problem here is that chemotherapy drugs are essentially poisons. They're poisons which kill dividing cells. And what you try to do is you try to thread the needle when you give traditional chemotherapy drugs to a patient, such that you give them just enough to kill the rapidly dividing cancer cells, but not enough to kill the cells which are dividing on the normal pace or not dividing at all. And that's a really, really tough needle to thread because, for example, hair follicle cells and the gut lining, these are cells which turn over all the time, which is why so many chemo patients lose their hair and have terrible nausea. So it's a really tough target to hit. And to get enough of a chemotherapy drug past the blood-brain barrier, you'd have to have it hit a really, really high concentration in the bloodstream before it gets through. And that would be incredibly toxic to the rest of the body. But there are some drugs, and one of them, for example, is a drug called irinotecan, which is pretty much completely inert until it's activated. And it's activated by being modified by an enzyme within cells. So if there were a way that you could give a patient with brain cancer, glioblastoma in this case, a really high dose of this drug to get it into the brain through the blood-brain barrier, that's fine. It's inert. It's not doing anything. But if you could find a way of converting it to the active form just at the site of the tumor, you'd be able to localize all the toxicity to where you want it. So Dr. Karen Aboudi at City of Hope came up with a pretty interesting strategy here. She took advantage of the fact that neural stem cells, and I mentioned them previously, have some interesting properties. They're pretty easy for us to grow up in large quantities. And for various reasons, they have this tendency to migrate towards tumors, particularly brain tumors. We can talk about why that might be later on. And you can also infect them with certain viruses. So she reasoned that if you took a virus, in this case, an adenovirus, which under other circumstances just causes colds and some other things, and you modify it so that it can encode the enzyme which turns that inert cancer drug into the active form, you could infect those neural stem cells with this virus, shoot them into the patient's brain, they migrate to the site of the tumor, and then you flood that patient with that drug. And you get it at a high enough concentration, it gets through the blood-brain barrier, but it's only at that active at the tumor site where these cells have migrated to that it gets converted into the active form. And so this is in clinical trials at City of Hope and elsewhere also. And my facility makes both the virus and the neural stem cells and the combined product, which is being used in these trials. So I've been talking kind of blithely about manufacturing viruses, and it's worth talking about how you actually do this. Viruses, as I mentioned, they can't do anything on their own. You got to grow up in cells, and viruses are pretty persnickety as to what cells they will grow in. And sometimes you can only grow them in cells which are happy when they're growing on an adherent surface, as opposed to cells in your bloodstream, which float around and grow very happily. But some things only grow on these cells which adhere to surfaces. So for example, on the left, we've got something called a 10-layer cell stack. And picture something which is about the dimensions, the width and the length of a cafeteria tray, but it's about 1.5 feet high. It's got 10 flat layers on which cells grow, and it's got media in between. So you can grow billions of cells in one of these. And we use these things to produce viruses, and we're typically using up to 40 of these 10-liter cell factories. So it takes a lot of space to do this. There are some other viruses which only grow in cells which don't want to adhere to things. They grow in suspension. So in some cases, you grow in these enormous bags. They could be anywhere from, say, 5 liters up to 50 liters to greater than that. So they're floating around in here, and you put them on these enormous rocking platforms that keep the cells floating and not setting out at the bottom. Or you grow them in these kind of flasks which have impellers at the bottom that spin and keep the cells in suspension. There's a variety of ways of doing that. And these are all great when you're growing viruses that have the capacity to replicate under certain circumstances. For example, vaccines. The COVID vaccine we're making at City of Hope is a great example. What you want is, at the end, is a virus which can infect human cells but not replicate and cause disease. Well, the vaccinia virus we're using is very, very picky about its host. It grows tremendously well in chicken cells. So we literally start with a bunch of ground up eggs, unfertilized eggs, and we harvest the chicken embryo fibroblasts in this, actually the fertilized eggs, pardon me, the particular type of cell called fibroblasts, grow them up to very, very large quantities, infect them with some of this vaccinia virus, wait till the cells are spitting out more and more virus, harvest that virus and purify it, and then it gets injected into patients as a vaccine. But because it can't replicate in human cells, it can infect and get its proteins in there and start stimulating the immune system, but it can't keep replicating, so it doesn't cause any disease, and it eventually goes away. In contrast, I talked about those oncolytic viruses that their whole function is to keep replicating, but only in tumor cells. So the way you grow those up is you infect what essentially are like cancer cells, large quantities of cancer cells with some of that virus. You wait till those cells are just exploding with virus and you purify them, and then you inject them into the patients. And again, they'll infect lots of cells, but theoretically they'll only continue to grow and kill the actual cancer cells. But I also mentioned some viruses which can't replicate at all. And I talked about the HIV-derived vectors, for example, in this case, where we want to retain their ability to transfer a payload, but we don't want them replicating whatsoever. So how do you grow up a virus that doesn't replicate? And the answer is you got to get tricky. On the left-hand side, I've got a really, really simplified version of HIV, and the black represents the envelope. So it's literally a membrane that the virus wraps around itself to protect itself. And I've got 4 genes inside there. And let's say this is the normal virus has got all the genes it needs to infect and replicate. In this case, the yellow gene represents the gene that actually makes the virus envelope, and the green gene there makes proteins that puts the whole virus together. And the blue and the red genes there in the normal virus would contain the genes that cause disease, that kill off T cells. But in our case, we swap them out for, say, something like a CAR receptor or something else, something therapeutic. So if you take this this virus and its genome, and you break it into its constituent genes, and you chemically introduce these fragments into your producer cell, the cell sees these gene fragments, starts pumping out the products, which are mRNAs and proteins. And the end result is that the yellow gene makes the envelope, the green gene makes the proteins that wraps that around the viral payload. But you wind up with a virus that has your payload, but not the other functions of the virus. So you have a virus now which can infect a cell, but can't do anything beyond that except introduce its payload. So we introduce these individual fragments of genes on pieces of DNA called plasmids into the cells. We harvest the remainder, and we harvest the virus they're spitting out, we purify it, and that's what we use to modify, say, T cells or NK cells. So I wanted to talk about what seems to be coming. So there's some things which pretty obviously they're in, say, middle or late stage clinical trials now. Off the shelf genetically modified cells for cancer, those NK cells I mentioned. There are people who are also doing some ingenious genetic modification of T cells. They actually make the T cells from stem cells, modify them so that they can kill cancer cells but not attack the host. Those are going in the clinic. There are gene therapies that are being tested in the clinic to cure sickle cell disease by modifying the patient's cells with viral vectors. Those trials have come to a screeching halt because there are some problems that we have to figure out. And I'm very involved in this process. And if there's time later, we can talk about that. There's a lot of things which are going to be derived from those pluripotent stem cells. For example, they're about to start clinical trials. A couple of different companies are going to start clinical trials with replacement beta cells to treat type 1 diabetes. So it'll be an unlimited source of beta cells. There's therapies that are starting up some clinical trials to treat Parkinson's disease with stem cell derived dopaminergic neurons. There's already clinical trials going on to try to treat forms of blindness, macular degeneration. We're producing those heart muscle cells I told you, and they will be used in trials to treat heart failure in different ways. And one approach is just literally injecting those cells into the heart to hope they'll sort of reseed the heart and reestablish good heart muscle. But we're also beginning to work with a German company which has taken these kind of cells and has made a piece of essentially engineered heart tissue, which will be sutured on to the surface of the failing heart. And they've started trials with this in Germany. And I guarantee you there are applications here I'm not thinking of yet because I don't know of all the technologies. And some of these things will work and some of these things will fall flat on their face. We don't know yet, but there's a lot of things which are happening in the cell and gene therapy world. So I want to close out with a couple of things. One is that I just get to give the talks. You know, there are a lot smarter, harder working people who are actually doing this work for me, and they're divided into various teams. Got a whole team doing the vector work and another team that's working on developing new processes for cell therapies, another making other cell therapies, and there's a separate team that works on processes to make viruses. So these are really hardworking, good people at City of Hope. We're looking to add some people to our team. So if you know people are interested, I'm glad to talk to them. I guess I'd like to say that when I started doing this job and people asked me what we did at CBG, my response was initially, well, we make weapons. We make weapons against disease. But as time has gone on and I've interacted more with patients and patient advocates, I realized I don't want to make weapons. Um, we want to create new therapies for patients with some really devastating diseases, and we don't want to manufacture weapons. We want to manufacture hope. And that's what we're trying to do here. And the last message I want to leave people with is that there are a lot of really brilliant scientists, clinicians across the world who are coming up with novel ideas on how to treat previously intractable diseases with cell and gene therapy. And our job, which we will continue to do with great excitement and great intention, is to help them take these great ideas and turn them into actual functional therapies that can cure people. So I'm going to stop it there. And if you've got any questions, I'd be glad to answer them.
So Brenda, you have some chat questions?
I can go ahead while we're waiting for Brenda.
Yes.
Oh,
Okay.
Brenda.
I was going to go back to the beginning and ask about the GMP facilities. Who actually does that certification? Or is it just a good practice that you incorporate yourselves in your own operations?
It's mostly that. We are inspected by the California FDA, essentially. There's no sort of national inspection process for GMP facilities. It depends on different societies you may be involved in. We've had the FDA come inspect us, but because we asked them to at one point, we were a new facility. Hey, are we doing things right? What should we do here? You don't want FDA coming to you uninvited because that means something bad is happening. So there's no really one accreditation body that does this kind of thing.
Whoops. Okay, great. Jeanette, you had a question? Go ahead.
Yes, I had a question about, are there any risks that some of these cells that you're mutating will continue to mutate? And if so, can they live in the wild or do they die immediately, or how does that work?
Well, the cells, let's divide that into two parts, the viruses we're making and when we've got modified cells. So the viruses we do are pretty much designed that they can't grow in normal cells. They've been modified in various ways, but we also have some pretty tight environmental controls, as you can imagine. We autoclave and bleach things, and we have things cleaned. We have the rooms periodically fogged with nasty chemicals, essentially, to kill off anything that might be in there. When it comes to the cells, the concern is always when you do genetic modification to a cell, is it possible you're going to do something you did not anticipate? To talk about what's happening with sickle cell right now, because I'm involved in something. It's a government-funded initiative called the Cure Sickle Cell Initiative. I'm involved in some work there. So there was some really big excitement about a cure for sickle cell, and the cure was to take, or may still be, to take a sickle cell patient's bone marrow cells. They're called hematopoietic stem cells, and infect them with one of these lentiviruses that's modified, in this case expresses a healthy globin gene. And it looks like it works, and that's all well and good. And these viruses that we're using have been designed so that they should not cause cancer, because the first generation of viruses which were used in some therapies, they were trying to cure kids with these severe combined deficiencies, these bubble kids, you're probably familiar with that. And these therapies worked. They cured these kids, but it turns out the earlier generation of viruses they used had this really bad habit of sitting down next to some of these cancer-causing genes and turning them on, so mutating them essentially, revving them up. So that was bad. So these viruses we've been using have been designed so that they can't do that, and they haven't done that. But very recently, a company called Bluebird Bio has been treating patients in a phase 1 trial with that approach. They one of these modified vectors into their cells. And interestingly, they're also trying to treat patients with a completely different disease called beta thalassemia. another case where patients don't have a good functioning beta globin gene, but it's a different kind of disease. It's caused by different ways. But theoretically, you could treat both of these with that same virus by putting a new globin gene into them. So what they found so far is that it's great for the thalassemia patients. Everything looks good. For the sickle cell patients, out of, I think they've 40 or 50 or so they've treated, at least one of these people has developed a form of leukemia, and another one has a condition which could lead to leukemia. Nobody in the other arm of the trial with thalassemia has developed anything like this. And right now they're trying to figure out, is it the virus that's doing it? There's ways of testing it, because if you look at the leukemias that arise, if you see, oh my God, every one of these cells has a virus in there that we put in there, that's a pretty bad sign. But there's concerns that, is there something different about the stem cells that you get from a sickle cell patient's bone marrow than somebody else's? There's also a concern about a really powerful drug called busulfan, which is used in transplant settings. So it's used to wipe out a patient's bone marrow, because when you replace their bone marrow with something, you have to sort of literally create space for that. And busulfan is a powerful way of killing off bone marrow, but it's a nasty drug. And there's some concerns that that could be so toxic that it's mutating cells and it's causing them to develop cancer in these sickle cell patients. And for some reason, their cells may be more susceptible. Nobody knows yet, but the entire field is sort of holding its breath, because even the other therapies to treat sickle cell, which involve genetic modification that may not use viruses, right now are still using busulfan to create space to reintroduce the modified cells. So everybody's very concerned about this, and the field is trying to get this straightened out.
So the other question I have is, in the heart failure situation, which I'm personally really interested in, are you essentially suturing new muscle to the heart? I mean, are you making the heart work more efficiently and increasing cardiac output, or how is that working?
There's a couple ways you can think about doing it. And one of the, full disclosure here, one of the reasons I left Stanford was I was being driven crazy by their approach to it in the Cardiovascular Institute. Back when I was at Geron, the biotech company, I'd actually figured out a way to make very large quantities of this heart muscle cells. What we're using at City of Hope now is a different, more evolved method. It's better than what I came up with. My method kind of helped start things, but the City of Hope method is much better, and I had nothing to do with that. But two ways you can think about it. One is that you just take a suspension of billions of cells, and you literally take a needle and start injecting it into different parts of the heart, and you hope that those cells survive and they engraft and they get functionally organized, because the heart is not just a collection of muscle cells. It's incredibly organized. There's a very, very complex architecture there. That's not an approach that makes a tremendous amount of sense in a lot of ways. So the other approach is to say, no, we're going to actually make an engineered chunk of muscle outside the heart first, literally cast these cells in a mold, mix them in various ways and shape them, and then suture that over the weak parts of the heart. Mm-hmm. And that's the approach that's being taken in some other places. And that, I think, is more likely to succeed than the other way. Yeah. I will also say that there have been the dirty secret of a lot of the cell therapy world is there's a lot of stupid things have been done. A lot of stupid things that I can't understand why anybody thought they would ever work. And for a while, there was this idea that you can inject all kinds of cells into the heart and they're all going to turn into replacement heart muscle. And it was just nonsense to start with, and none of it worked. But people did it for years and years and years and try to convince themselves they're seeing something, and they're not. These are the first attempts to take bona fide new heart muscle cells and put them into the heart. So this could do something different. I'm just a little suspicious of the notion they will automatically arrange themselves in beautiful architecture without some help.
Thank you.
Joe, let's talk about some of the operational things before we get back into, there's a bunch of more highly scientific questions, but from the operational perspective, there's two questions. One is, Joe is interested in knowing if you're using any of the local packaging people to package up any of your products. And Chris wants to know what your procedures are for access to your facility.
So I need to stress that we're sort of niche manufacturing. We're not making products which the FDA has approved yet. We're making things which are in clinical trials and hopefully will be approved. So we're not making commercial products. So the things we're making typically are being sent by special carriers, to clinical sites. They could be frozen cells, they could be frozen viruses. Sometimes they're live collections of cells or engineered tissues or things like that. But we're using specialized courier services for that. So that the packaging is, you put them in a temperature controlled shipper, you put a temp tracker in there, and you get qualified shipper to transport it. So, when we get to something which is more commercial and reproducible and less, I don't know, less fine craft and more mass manufactured, that's when we'll be able to use, packaging and shipping services. And I think the other question was about access to the facility. So everything is key card. So people only get access to the parts of the facility they should be in. There's different levels. The people who work on the cell therapy side can't immediately go into the side of the facility that makes the viruses, and vice versa, to keep things from getting mixed in that way. I run the facility. They've never let me into the virus part of it yet. So sometimes I have to put my foot down and say, damn it, let me in. But I know what goes on there, and they're my teams. But sooner or later, they're going to have to let me in. They have to decide that I have a high enough clearance that I can do it.
So I guess another access question is, what about, you say you're working with a German company, City of Hope has got its own internal customers, but how much do you, either now or in the future, think of yourself as a service provider to the greater community for this stuff?
So that's a great question. And one of the things that makes us unusual is that we are both a core facility for City of Hope. So we're manufacturing viruses and cell therapies for them, but 50% or more of what we do is for outside clients. And those could be for other academic groups or startup companies, or in one case, one very large player in the CAR T space. So we're both a combination core and a contract manufacturing organization, which is a schizophrenic thing to be at a not-for-profit. We want to do both types of things, and a lot of the regenerative medicine work we do, the heart failure, some of the other diseases, graft versus host disease, and ALS and that kind of stuff. That's not really typically part of City of Hope's mission, but because my long history as a cell and developmental biologist, I've worked very closely with the California Institute of Regenerative Medicine, for example. So they send people to us all the time who need help making their new therapies for these various diseases using cells. We also work closely with the National Heart and Lung and Blood Institute, which is one of the reasons why I'm so involved with sickle cell, but some other things too, like the cardiomyocyte work, that kind of thing. So we're very broadly networked, supplying, and we have different rates really, not-for-profits versus for-profit companies. For City of Hope investigators, if we were purely a company, we'd go broke because we have to heavily subsidize everything we do for them. That's fine. You expect to have to do that. For outside academic groups and not-for-profits, we have to charge them something. I try to hold it to what I can. And for external companies, if I think they can afford it, I'll charge them what I can get away with to feed back into the system to subsidize the rest of it and do it with no shame. And so far, for example, the viruses and things we've made for outside companies, they keep coming back because they like the quality and they're willing to pay the price. So, we'll see if we can get away with it.
You are a scientist of the market economy, Joe.
There you go.
We've got some questions about some of the other projects that are going on at the City of Hope. People are interested in knowing if there are more about the COVID vaccine trial, as well as any other clinical trials that might be going on the TP53 targeted therapies or anything else out there. And I will, if Chris wants to unmute and follow up on the details of her oncolytic viruses that she's talking about, we can follow up with that. But let's start with what you know about the COVID vaccine going on at the City of Hope.
Sure. So the COVID vaccine, again, we're starting with this kind of virus called modified vaccinia. And it's a virus which has been used in the past to actually make a successful Ebola vaccine. But it's a virus which has been heavily mutated so that it can't cause disease, and you introduce the fragments you want. And Don Diamond's team has introduced fragments from 2 different COVID virus genes. There's something called the spike protein, which everybody's concerned about. It's the protein which the virus uses to latch onto the cell surface that it infects. And when you're talking about these viral variants out there, what you're really talking about are viruses which have mutated spike proteins that have changed such that they look different from the original, and antibodies that might bind against that original form might not be able to recognize that same new version. So this virus that we've made contains the spike gene and also another gene, a different gene that helps make up the virus shell in this case. And the idea being that it should stimulate not just antibodies against the spike protein, but both antibodies and T cells against the spike protein and this other protein, sort of a double level of protection. And it works really well in animal models, and it's going through a phase 1 trial right now where they're giving people different doses. And the goal of any phase 1 trial is always just to make sure it's not doing any harm. And you will, for any kind of cell or gene therapy, you'll always see people do a phase 1 trial. And typically, if there's no harm, which is great, you'll always see, well, our trial was not big enough to show an effect. It wasn't designed to be big enough because we need to have X number, hundreds of thousands of patients to really show it. But we see very encouraging trends. And that could be true, but I can't tell you how many trials that I've seen where that very encouraging trend in 10 patients or 15 patients, by the time you get to your phase 2, which might be hundreds of patients, suddenly that effect isn't so large or not so observable or fails at phase 3. So the City of Hope vaccine right now is in phase 1. So far, so good. They're monitoring people's immune responses, but there's a placebo arm here still. So it's well behind the approved vaccines. We were probably going to wind up making another version of this vaccine, which will include some of those variant spike proteins. So it's sort of like a booster to help stimulate the immune system against these other forms of the virus. That'll probably go into clinical trials alongside this one too.
And do you think that the variant work, that whatever you're working on is going to be able to work with the people that have had Moderna, Pfizer, J&J?
So it's a great question, which is being considered in a lot of ways. So I mentioned that a perfect vaccine would sop up the infection before it happens. The antibodies that we have as a result of these the vaccines now, in a test tube, you might find that for some of these variants, it takes a lot higher concentrations of those antibodies to work. And that's because, the spike protein has changed. It's not exactly looking the original way. It's kind of similar. And if you pump in enough antibody, eventually the antibody will recognize it and stop it. So it's important to remember that this is not the end of civilization. It doesn't mean that all the vaccines out there are going to fail against all the viruses. It's one thing to compare what happens in a test tube versus in people. And none of these things take into account that T cell response I was talking about. So even if the antibodies don't work as well as we want and people still get infected, there's every reason to think the T cell arm of the vaccine is going to keep you from getting tremendously ill. So yeah, it'd be great if these things stop anybody from getting infected, but if these vaccines instead said, when you get it, you get the equivalent of a mild cold instead of a deadly illness, that's still a win all around. And so I'm not willing to panic over this. Let's put it that way.
Well, that's good. Chris Curry, did you want to unmute and talk more about the oncolytic viruses and the questions
Sure.
that you had?
Hi, Joe. Can you hear me?
Sure, Chris. Yeah.
Hey, so a couple quick questions. They may be outside your purview. Do you know if the TP53 targeted therapies are in vivo or in vitro in studies, or are they already out in clinical trial at City of Hope?
The sort of P53 vaccine trial or the oncolytic vectors?
Either.
The vaccine against P53 is in clinical trials at City of Hope and probably elsewhere, and we can find those trials. Sorry.
Okay. And are the other oncolytic viruses that you guys are looking at, are they potentially for people with metastatic disease instead of early disease that they're trying to prevent from occurring?
I think at this point we don't know what they'd be best at. So some of the early trials for some of these oncolytic vectors might wind up being in things like liver cancer, but it's not clear. They're really searching for the best tumor types to try this on. And at a different level, we're about to get involved in a project which is when I told you your immune system, why isn't it recognizing these funny cancer proteins? What's happening here? Well, it turns out that in a lot of cases, immune cells actually do start to invade a tumor, but stop. They don't do anything. And it turns out that's because tumors evolve ways of shutting down an immune response, just keeping these things dormant. Well, there's some evidence that if you get a chunk of the tumor and you find a way to pull those immune cells out away from the influence of the tumor, there are ways of essentially activating those cells. Because these are the cells that specifically went to the tumor in the first place. If you can turn them on, they're likely to be highly selective for that tumor. So you turn them on, re-educate them, put them back in, and they should attack. And when it comes to things like these oncolytic vectors, one thing that's been very interesting to see is that things seldom work the way you think they're going to. So the simple model for the oncolytic vectors was, if you've got metastatic disease, we're going to inject it into you, and that virus is going to go and it's going to infect every tumor throughout your body and it's going to kill it that way. Well, it turns out some experiments have shown that, yeah, you have cases where the virus is locally injected into a tumor. So it can't spread throughout the body in a metastatic model, and it definitely infected that tumor. And that tumor dies, but the metastases die also. And the reason that appears to be that when these viruses are killing these tumors, everything they've been using to hide the immune response, to damp down the immune response, just goes to hell. So it doesn't work anymore. So the T cells that have been trying to kill this tumor and have been able to are now unleashed, and they go out and seek out the tumor throughout the body. So it's a very interesting how a localized effect can be a systemic effect in ways we don't anticipate. So there could definitely be a role for these in metastatic cancers.
That's fantastic.
And following that up on that, Victoria, you might want to jump in. Her question related to that is, with these tumors, if you've got a patient that's operating in a moving fluid, as some of the other diseases might be, what impact that would have. And Victoria, I will allow you to elaborate on that more with your leptomeningeal
disease. Yeah, I think you answered the question that the different types of tumors are still being figured out as to how it's effective. I mean, leptomeningeal disease, as you know, is like one of the most ominous prognosis that someone can get, because it's in the spinal cord fluid, and that fluid is then encasing the brain, and it makes the tumors travel all over. So it's a moving target. Like those tumors just aren't typically able to be treated with radiation and things like that because it's moving. And I just was curious if this is one of those potential breakthrough things that could be helping with such a horrible cancer.
I think anything that can treat a widely disseminated disease, whether it's a virus or the whole Trojan horse strategy, theoretically could. Now, I have to say something, what I should have said at the beginning. Nobody should mistake me for a physician, right? I'm a misplaced cell and developmental biologist. I'm a simple country developmental biologist running a GMP facility. So, don't take what I say as gospel, but there are more and more approaches out there which are designed to try to tackle these diseases. I could not give you a summary of that particular one, but I know some work like that is going on at City of Hope.
Thank you.
What is the relationship between CRISPR and all this stuff you're talking about? Because you haven't mentioned CRISPR per se. Is it always or often there and just part of the toolbox?
It's a great question. So there's a couple ways you could modify cells. And one way, the original way people did it was they essentially used chemicals to try to get new genes and things into cells and hope the cell took it up and hope the cell took it up in a useful way. And that worked a little bit. And then people figured out how to use viruses to deliver genes. And that's great, right? The problem with viruses, they can be very efficient at delivering, but you don't just get your therapeutic genes. There are some other parts of the virus that have to come with it. They may not cause disease, but if this virus decides to set down its payload, in the middle of a critical gene that keeps your cell alive, well, that's not very helpful, right? Or like the earlier cases where kids were getting cancer because these viruses sat down and some of the sequences in the virus activated oncogenes. Bad, right? So people have long been searching for ways to make very, very precise edits to DNA that don't involve viruses. So in the perfect world, you'd make your alteration and you'd get out and there'd be nothing but that alteration left. So CRISPR is a way of doing that. Originally, it was identified first as turns out to be E. coli's immune system. You can think of it that way. It has these really remarkable characteristics that it can cut at very, very specific parts of a gene. And you can design exactly what parts of the gene it's going to cut at, down to the base pair. It's basically a pair of scissors with a guide, and you create a guide which binds to the particular gene region you want, that it brings the scissors along with it and it cuts. And it turns out when you do that, and you just introduce that in the cell, a couple of things can happen. It can cut, and if there's nothing else going on, the cell says, oh my God, there's a cut in my DNA, I'd better try to do something with it. And sort of nibbles away with it and tries to fix it. And it just cuts a chunk out of that gene. So people do that as a way of trying to shut down genes permanently. Good example, another approach in sickle cell is that you could theoretically cure sickle cell if you could turn on a different globin gene. in these patients. And there's a fetal form of globin which could stop the effects of the sickle cell gene, but it's repressed, it's turned off after birth. But it's turned off by a particular stretch of DNA. And if that piece of DNA were disrupted, the gene would turn back on. So people are using CRISPR targeted at that point, say cut there, the cell kind of chews it away and it no longer has that sequence, the gene gets turned on. But the other thing CRISPR can do is if you cut a very precise place, you can introduce a piece of DNA to insert directly into that site. And for example, you could pick a particular gene and say the sickle cell gene and say, wow, there's a mutation there. That's a bad amino acid. You could stick in a piece of DNA that is the normal sequence. And if you cut it with CRISPR right at that site, it cuts there. And with a certain frequency, the cell replaces that damaged part with this new piece of DNA you put in. So now you have a perfectly restored gene. And there's ways of trying to get that more effective. And people are concerned about making sure it's as precise as you want it to be. But it all depends on how you can get the CRISPR enzyme and your what's called a guide RNA into the cell. And sometimes you use harmless viruses. There's a virus called AAV, which infects cells and then goes away. There's no virus DNA left. It's a good way of delivering something. Other people are using chemical ways of trying to get it into cells. And if they can get this to work right with no viruses, you can make any change in a cell you want as precise as you want and not worry about side effects. And there's a lot of research going on at that, including at City of Hope.
One of the other, given that kind of cell manipulation, Joe's asking an interesting question. Do you get much pushback from anti-stem cell people or anti-vaxxer type people? And how is it that you handle that?
That's a really good question. Now, I will tell you, I have not personally had to deal with any kind of anti-vax stuff. When we were working at Geron, in my early days, we were the people who actually funded the isolation of the first human embryonic stem cells. And I was the first scientist to work with those cells. I didn't derive them. There was a guy named Jamie Thompson at University of Wisconsin who came up with a way of culturing these cells. And yeah, there was all kinds of hell. This was in in the mid 90s or so. We had protests. We had people accusing us of things. I once gave a talk at a scientific symposium attended by a lot of clinicians, and I said, well, we're trying to treat spinal cord injury with these cells. We want to take these cells and turn them into the oligodendrocytes, the insulation cells of the spinal cord that get damaged. That's why people get paralyzed. The cord doesn't get cut. It's the insulation of the cord that gets destroyed and doesn't grow back. I talked about this, and there was a surgeon in the audience who stood up and said, I think what you're doing is wrong and you have to be stopped. And which is a novel response to get in the middle of kind of a scientific talk. And we talked afterwards and had a good dialogue about it. But the thing is that for all the controversy over embryonic stem cells, in the early 2000s, there was an amazing scientific breakthrough. A guy named Shinya Yamanaka figured out how to take a normal cell, it could be a skin cell or blood cell, and by, at the time, introducing 4 genes into it, turning it into something which was essentially an embryonic stem cell. It did everything an embryonic stem cell did, but didn't come from an embryo. And that technology has been refined, and it's being used all the time now. And one way it's being used is if I wanted to make heart muscle that, for you, that wouldn't be rejected, we could theoretically start with one of your skin cells, reprogram it to make it into a stem cell, turn that into your own heart muscle, put it into you, no rejection. There's other ways that people make these stem cell lines and modify them in ways so they could be accepted to more people. So in all honesty, there's not a lot of reasons to keep working with embryonic stem cells. It's all the methods we used to make them grow and differentiate into the tissues we want. They work exactly the same way for these other cells, which are called IPS cells, induced pluripotent stem cells. So we hadn't done the early work, you couldn't have come up with the IPS cells. So it served its function, but there's really no reason to keep using them.
That's interesting. Now, that level of innovation, Brian is sort of addressing. Now, remember, Brian is our Economic Development Commissioner, our great economic volunteer. But he's curious about the level of innovation today as compared to 10 years ago, and what policies and practices are contributing to our current levels of innovation, or I should say your levels of innovation. I don't feel very innovative in this topic at all.
Well, what's interesting is that the gene therapy field hit a wall in the early 90s. There were some bad outcomes, and the whole field came to a screeching halt. and it was kind of off the radar for quite a while. And then suddenly there were some academic groups, notably at University of Pennsylvania and Memorial Sloan Kettering, who figured out this whole way of modifying T cells with these viruses. And the field just exploded after that. And suddenly the field leaped ahead in ways. People thought that cell therapies were going to come up sooner than they did, but these new genetically modified cell therapies just burst to the fore. There was so much good science around these kind of things and so much investment in it now. And with tools like CRISPR, which really are game changers, it just allows you to do things we never thought we could do in ways which we think are much safer than anything we could ever do before. It opens up amazing possibilities. Now, in terms of policies and things that affect it, I will tell you that one thing which is interesting when you work at universities now is this obsession with China. You know, Chinese scholars that, oh, they're coming, they're going to steal our things, that kind of thing. And you know, it's not been infrequent that Chinese companies are known. The Chinese government is known for essentially usurping technology. If you want to file a patent or something in China, they really want information they're going to use. But the Chinese scientists we work with are some of the best in the world. They've made amazing contributions. And this kind of witch hunt over it's a Chinese scientist, it's probably a spy for Beijing. It hurts everybody. You know, it's hurting people. It's stopping the field from advancing as fast as it could. That's one thing I'd point to as a negative kind of thing. Let's put it that way.
Okay, well, I don't know, how do you have a lot of the questions, or normally we do this for an hour and let the presenter.
No, unless I have done injustice to any of the questions on there or forgot one, I would suggest you unmute and ask it now. But I think that we've generally covered everything that was up there.
Scream next time the federal government cuts the NIH budget. That's what it is. You know that, so me with my Swiss background, I can compare the numbers. In Switzerland, basically the first starting grant for a lab, which is the R01 here has like somewhere between 15 to 20% success rate. In Switzerland, it's about 46. And that's the difference. That's where your innovation comes from, because you can't tell what type of research is going to lead to something that's going to be useful. And CRISPR is the perfect example for that, actually. So I was, ironically, I was around at Berkeley while Jennifer was playing around with CRISPR, and the word going around at Berkeley was, why are you studying this weird stuff? You know, these stupid bacterial defense mechanisms.
Nobody cares.
This is some idiotic process that happens in bacteria. Why do we look at that stuff? That doesn't make any sense. Take it, move on. And that was, by the way, by Berkeley faculty, by people who should have known better, who actively discouraged her continuing her research. And here we are, right? 10 years, 15 years later, and you never know. So it's government funding that fuels that innovation.
It's seed funding, like anything else. Let 1,000 flowers bloom rather than 100 flowers bloom. You get a better outcome.
Yeah. Unfortunately for Jennifer Doudna, who won the Nobel Prize for this work on CRISPR, she also was talking like a scientist and saying, well, yes, we've done this in bacteria. We don't know for sure that it can be done in mammalian cells. And apparently the patent offices have caused a lot of trouble, because the people at MIT were able to get patents as well, because they were able to do exactly the same thing. And of course it worked in mammalian cells just as well as it worked in E. coli. But she was just being careful and a normal scientist. But anyway, it's one of those, you know, great stories that I just know from the IP side.
Yeah, you're right. You're right.
Yeah.
He still came out okay, as it turns out.
Everybody's going to be okay here, and I hope it's going to work.
Yeah.
Well, one of the questions I always kind of had, or my question about innovation was kind of the concept of Moore's law in the silicon industry. I'm wondering if in the bioscience, biotech side of the world, could we say we're entering kind of a Moore's Law era?
That's a really interesting thought. I hadn't thought about it that way. There are certain things which are causing major advances. CRISPR is one. Some things which you would not think of being major technical challenges turn out to be huge ones. The whole thing I talked about coming up with new beta cells to treat diabetes. And it wasn't that people couldn't figure out how to make beta cells. There's better ways of making than we started with, but nobody could figure out how to get these things to survive when you transplanted them, because they were immediately attacked by the host's immune system. First of all, it's a foreign beta cell. Also, in a type 1 diabetic, the reason they lose their beta cells, it's an immune system attack on their own beta cells. So it's a double whammy. So people tried to figure out, can we put these cells in but protect them in some way? And they tried to come up with various little types of pouches, really, like a tea bag, that would allow blood and insulin and things to go in and out, but keep out immune cells and antibodies. And it took forever to come up with a way to make that work. And there's been a company that's been trying to run a clinical trial since way back in the 90s called ViaCyte, trying to get their technology to work. And only recently have they been able to come up with a way of keeping the cells alive. And other companies have kind of leapfrogged that in some ways. So it's just a pouch. Why should that be so hard? But it turned out to be incredibly difficult.
Okay, well, I'm going to go ahead and we're going to have a networking after this, but for those that are signing off, thanks for joining us. And we're going to be back again next Wednesday for Me Industries. So hope to see many of you then.